Thank you for viewing this recorded Reliable Automatic Sprinkler Company webinar. Should you have any questions regarding this presentation, please feel free to contact Reliable Technical Services at 800-557-2726 or email us at techserve@reliablesprinkler.com. For upcoming webcasts and an archive of past webcasts, please visit reliablesprinkler.com/webcasts. Once again, thank you and enjoy the presentation.
Well, thank you for the intro and thank you to those attending. Today we're going to talk about tunnel fire protection. This is Reliable, so we're going to focus a lot on water-based fire protection systems, but we're going to talk a little bit about the total package of fire protection that goes into tunnels and why it's needed. So to kick this off, let's talk about the fire. So we'll start with this image. So it's a car fire, as we can all see, and in and of itself, maybe not the biggest deal in the world. It's outside, heat's escaping. As long as the passenger and the driver got themselves out of the vehicle, no one's close to it. And even if you were, you get 25 feet away, probably not that big a deal because all the heat and the smoke are rising up away from there. Nothing's trapping them. Doesn't seem to be any wildland fire threats. Everything's pretty green and lush and wet there. And I think a fire like this, the fire department shows up and they'll have a pretty good time with being able to deal with this, get it cleaned up, and get this road back in service. So car fire in and of itself, out in the open, maybe not the biggest deal in the world. So let's take that car and put it into a tunnel and talk about what happens then. So we take that car, we put it into a tunnel, all of a sudden we have the surroundings of the tunnel that do several things that make the situation a whole lot worse. One thing that they do is they trap the heat, trap the smoke coming from the fire. And so that smoke is then spreading along the tunnel, obscuring the lighting, making egress from the tunnel and evacuation much more difficult. The other threat there is that the smoke coming out of that fire, well, has an awful lot of toxic gases and things in it that you don't want to breathe and aren't good for people. So we take a fire that's on the outside, not really a big deal, have to deal with it, treat it seriously, and we put that in the tunnel, and all of a sudden we have a situation where the smoke from the fire is trapped, it obscures the lighting, makes it more difficult to see, makes it more difficult for the occupants to get out, and also is a hazard to the lives of anybody in that tunnel. So what does the tunnel remind me of? Well, when I look at a tunnel like that, it kind of reminds me a little bit of a pizza oven. Take a tunnel like that with a fire in it, and it looks an awful lot like this wonderful brick pizza oven that's creating some great pizza. And what happens in this oven? Well, we have a fire on the one side of the oven. That fire heats up the bricks on the top of the oven. Those bricks then radiate the heat down and cook the pizza in a split second. So let's go back into the tunnel and look at that. Same thing happens. We put a fire inside a tunnel. There's a car fire in a tunnel. At some point, the top of that tunnel and its materials heat up. When they heat up, they then re-radiate that heat back down onto the vehicle. So that's got several problems. One is anybody who's in that space, whether they're first responders or occupants, passengers of those cars, well, they don't need to be in that area because they're going to have some challenges. The other issue is that heat bouncing back off of the tunnel is going to make the car fire worse. And so the heat coming back down to the car fire tends to make the car fire itself increase in size because it's receiving more heat to make more fuels come off of it. So that fire we take from the outside where it's not as big a deal, and we put it into a tunnel, and all of a sudden it goes from well, not so terrible to much, much worse. Now, so far, we've just looked at one vehicle inside of that tunnel. Now, we don't put tunnels out in the middle of nowhere typically. For the most part, tunnels are built in places where there's significant traffic, and they're put in places where there would tend to be a lot of cars in usage, right? They're relatively expensive infrastructure projects. We typically don't spend that kind of money no place in the world unless it's going to get significant usage. So the image on the screen here shows a tunnel. Well, could be rush hour traffic, could be some incident ahead, who knows, but there's an awful lot of cars in there. And that makes the situation even worse because we have a lot of people who are going to need to be able to make their way out of there. We have the potential for a fire that spreads between cars. So if we have one car have some issue, fire starts, fire grows, there's a bigger chance for the fire to spread from one car to the other and to have an even larger fire. The other challenge here is if we look at this, we have first responders who are supposed to get back to deal with that fire incident, and they're going to have a challenge getting to it if they have to make it through traffic to get there. And let's make the situation just a little bit worse, and let's say that instead of a car fire, let's say that we have a cargo truck with some contents in it, and that's the source of our fire. So now we have a much more significant fire. So in terms of first responders, they do a great job of dealing with fires, and they have a much better situation in doing that when it's out in the open. We talked about all these situations where occupants can be exposed to toxic gases, significant heat inside a tunnel during a fire. Well, firefighters have to deal with the same thing. And so you take them from a situation outside where they can see what's going on, they have easy access to it, and you put it inside a tunnel where access is much more difficult. Their, ability to see what's going on is restricted, much like the occupants. And there is a limit to turnout gear. And so they put their turnout gear on, they go in to deal with the fire, but turnout gear will not deal with all situations in the world. And some of the temperatures that we see inside a tunnel fire are higher than you can deal with typical firefighter turnout gear. So it's very, very bad situation potentially. And the question is, well, does this happen? And the answer is, well, when it does, you find out about it. If we have a tunnel in a city and there is a fire incident in that tunnel, it most definitely will hit the news. It's a significant event in that city. And I think when we look at it, one of the things that'll come up here when we talk about protection options, the question at that point is we have a significant disruption to the city. How quickly can we get it back online? Because if you take a major artery out of a city's roadways for any amount of time, even a temporary shutdown, it can create some substantial traffic conditions, substantially impact commerce in that area, and is a major issue for the city itself and a lot of its residents. So when there's an incident in a tunnel, whether it be a fire or an accident or something else that shuts it down, the question is, how many minutes will it be until we can get this tunnel back into service? So as we talk about protection options for tunnels from fires, one of the things that we should think about is, it's one thing if we get all the occupants out safely, which we absolutely want to do and need to do. The other thing to think about with tunnels is how quickly can they be put back into service after the fire is addressed. So we address the fire department comes and puts it out. Finally, occupants escape before that. And then what are we left with in terms of the tunnel infrastructure to be able to get it back in service and get going again? So does this happen? Right, so we talked about this very difficult situation of having a significant fire inside a tunnel. And the question is, well, okay, is this just fantasy of things that could possibly happen, or does this actually happen? Well, let's start out with a big one. And we're going to go back a little ways. 1949, the Holland Tunnel. Holland Tunnel's in between New York City in New Jersey. Goes between right about Soho over across to near Newport Center in Jersey City. That tunnel's been around since the 1920s. In 1949, there was a truck going through the tunnel with metal drums of hazardous materials, and one of the drums fell off the truck. That started a potential explosion, a giant fire that demolished about 600 feet of the tunnel interior. And that's what's reported by the Port Authority that runs and operates that particular tunnel. It took 3 months to repair the tunnel. And if you go online, you can find the Port Authority's records of that particular event, and it was just tremendous devastation within the Holland Tunnel as a result of one truck going through the tunnel with, quite honestly, materials that probably shouldn't have been there. We're going to fast forward a ways because we're not going to do a full history here of all the tunnel incidents that are out there, but I'm going to hit a major point in time when we had a number of tunnel fires one year after another. So 3 consecutive years, 1999 through 2001, there were 4 very significant tunnel fires in that time span. First one, very well known, the Mont Blanc tunnel between France and Italy, killed 39 people, shut down a major roadway, European roadway, for several months. And one thing you'll notice here in the background, you'll see a pile of flour and butter. It's almost time for lunch where I am, but that's not what it's about. And it's actually a little bit not completely accurate. The Mont Blanc tunnel fire started with a truck that had margarine and flour, not butter. So something that, you have in your house. Grocery stores have a lot of it, other spaces. Seems like not that big a deal. Well, a truck carrying margarine and flour was the source of a tremendous fire in the Mont Blanc tunnel that claimed 39 lives. That same year, another fire in Austria killed 12 people. Significant fire the following year in Austria in a rail tunnel killed 155 people. And then the Gotthard Tunnel in Switzerland had a fire in 2001, killed another 11 people. So we're talking here about the lives lost, very significant. In addition to that, there was also major disruption to infrastructure in all the road tunnels here and transportation and commerce in Europe. So that was a 3-year span of, there's not that many significant road tunnels in the world. And we had a span of 3 years where in each of those years we had a significant road tunnel fire happening. So as you've heard so far, and you'll hear a little bit more here, tunnel fire protection is a very global topic. So, there are certain types of buildings where we see thousands of them each year, right? Warehouses, residential buildings, office space. There's probably people on this call who work on several hundred of those individually each year. And so those tend to be a little bit more local. There can be local methods developed that are tried time after time. And with tunnels, I think we find that it tends to be a little bit more global. There's just not that many tunnels built each year. But on the other hand, each tunnel that's built is a very, very significant construction project and a significant asset for the location where it is. So let's talk about some standards, and we're going to go a little bit around the world with tunnel standards here. I'm going to start out with NFPA and NFPA 502, which is their standard for road tunnels, bridges, and limited access highways. So NFPA 502 has a variety of fire protection features required. I'm going to go through this one in a little bit more detail, and then when we do the other standards, we'll touch on them a little more briefly. So one of the key features in NFPA 502 is it's intended to protect the structure, and part of that is to make sure there's no collapse or other event like that, which would be a big problem. Also looking at making sure that tunnel infrastructure can get back into service quickly. There's fire alarm and detection features sometimes required, emergency communication, make sure that the occupants can be notified and direction can be provided. There's traffic control measures, and as we saw earlier in one of the slides, if there's a fire and traffic has to stop, it's a significant issue to be able to get cars diverted away from that tunnel, get cars in other areas so that first responders can get there and so that occupants can get out. So traffic control is part of the safety, significant part of the safety in that tunnel. Standpipes and fire hydrants are included in the requirements. There's requirements for fixed water-based firefighting systems, emergency ventilation, and we're not going to talk about this too much today, but just want to realize that when we talk about tunnel fires, one of the areas that was significant originally became much more significant after the 3 years of fires that we talked about earlier is emergency ventilation, to help make sure that the smoke from the fire stays away from the evacuating occupants and the first responders to help everybody get out safely. And so that's an area of design that's very significant. A lot of engineering firms that spend countless hours designing those systems, and those are very, very significant smoke control systems that are often included in tunnels. Drainage is a big deal in tunnels. Got to get the water out of there that comes in. And then there's, of course, means of egress requirements, and that's helping the occupants of the tunnel, the passengers and the drivers on the road and the vehicles to get out. So what are we going to focus on today? Well, we're going to focus on, of course, the fixed water-based firefighting systems because, after all, this is reliable and that's what we do. So NFPA 502 has some requirements for fixed water-based firefighting systems, and that includes them in Category C and Category D tunnels. And what does that mean? Well, that means that fixed water-based firefighting system is required in a tunnel that's greater than 1,000 feet in length or 300 meters. Now, that's a direct prescriptive requirement. NFPA 502 and the other tunnel standards that I'm going to talk about are somewhat to different degrees, but particularly performance-based, particularly compared to some of our building codes here in the States and elsewhere, very performance-based. And so even in a shorter tunnel, shorter than 1,000 feet or 300 meters, fixed water-based firefighting systems may still be provided to meet some performance objective. Let me give you an example. So let's say that an engineer is designing a emergency ventilation system for a tunnel. The fan capacity required for that emergency ventilation system is probably going to increase as the potential fire size increases. So as a method of limiting the required size of that emergency ventilation system, they might provide a fixed water-based firefighting system in the tunnel, even for a tunnel shorter than 1,000 feet. Likewise, maybe there's a structural fire protection issue where the concern is that the structure would heat up beyond acceptable criteria if the fire is left to burn on its own without any type of fixed firefighting. And so even in a tunnel shorter than 1,000 feet, 300 meters, fixed firefighting system might still be required. That gets down to the particular analysis for that tunnel. For all tunnels built to NFPA 502, once it gets past 1,000 feet, 300 meters, they end up with a fixed water-based firefighting system. So as I mentioned, the criteria in a lot of these tunnel standards are very performance-based, and particularly the design criteria for the water-based firefighting system is very performance-based. It's not like going into NFPA 13, where we can look in there and identify our occupancy and find our appropriate design density and design area and design our system and have our spacing rules based on that. NFPA 502, much more performance-based. It expects the designers to develop design objectives for that system. It expects those designers to come up with some method of performance evaluation for that system, water-based firefighting system, and then develop the appropriate documentation, have discussions, and submit all of that to the AHJs, and make sure that that's all approved as part of the process. NFPA 502 lets the designer pick the appropriate installation, inspection, and maintenance standard for the water-based firefighting system, and it gives a very extensive list of options, even going so far as saying other equivalent international standards. And so it doesn't limit the designer to NFPA standards as the basis for the fixed water-based firefighting systems. It says sort of whatever's appropriate. I think part of that is trying to be a very global standard in a global construction market for tunnels. What we're going to talk about today is the most common system and application for tunnels, which is a NFPA 15 water spray system. But you'll notice that there's things in there like water mist and foam and wetting agents and even NFPA 13 automatic sprinkler systems. But for the most part, when we see tunnels, they have deluge water spray systems used to protect them. So NFPA 502 does give objectives for the water-based firefighting system. Those objectives, though, somewhat broad. One of the objectives is to slow, stop, or reverse fire growth. And it has a phrase, and I've rephrased it a little bit. This isn't exactly what NFPA 502 says, but it kind of basically gets to the point of, or do something else that's helpful. And that's, whatever the designer of that particular tunnel thinks is necessary for that system to do, they can design it to do that. So some of the potential objectives are improving tenability for occupants, assisting first responders, or, as I mentioned earlier, providing for structural fire protection. So what's my spacing? What's my design density? How do I do my system? Well, NFPA 502 tells you some things to think about. It identifies layout parameters, does not give you any specific requirements for coverage or spacing, pressures, flow rates, any of that kind of information that we typically go into NFPA 13 or sometimes in conjunction with the manufacturer's literature to get. And so it doesn't give anything specific. It gives a list of parameters to consider that need to be addressed. And it suggests that they need to be based on code standards, accepted practice, or engineering analysis. So the most important one, I think, and the first question is typically, well, what's the required water density? I'm designing a water-based fire protection system for a tunnel. What's the required water density? Well, NFPA 502 doesn't say. You base it on some code standard or typically an engineering analysis, and that water density will a lot of times depend on the design objectives. So if all we're trying to do is maybe cool off a piece of structure, that can a lot of times be a much lower density than's needed to actually put water on a fire and suppress or extinguish it. What we find is that the required density tends to vary by region somewhat, but there's a couple of references here on the screen for some work that has been done to look at different potential water application rates and their effect on vehicle fires. I'll just say for our purposes here, they end up at about, in their terms, 10 millimeters per minute, or in more typical terms here in the States, 0.25 GPM per square foot as a good density to help to suppress the actual vehicle fire in a tunnel with a water-based system. So nothing specific is provided in NFPA 502 for water density. There's some references here on the screen available on the internet. You'll be able to find them to help you come up with an appropriate density if you're working on a project like that and need to do it. And for summary for our purposes here, a lot of what we're going to talk about in the rest of this is a density of about 10 millimeters per minute or 0.25 GPM per square foot, which is mentioned in each of these studies for different purposes. So one of the very important parts about these systems in the fixed water-based firefighting system is the drainage. Tunnels are required to have drainage by NFPA 502, and that drainage needs to be of sufficient capacity to receive the rate of flow from all roadway sources without flooding the roadway. So what does that mean? Well, if we have standpipes in the tunnel, and we probably do, it needs to be able to collect the standpipe discharge, needs to be able to collect fuel spills or hazardous liquid spills, needs to be able to deal with environmental sources, and that means if it's near the entrance to the tunnel, for example, rainwater coming into the tunnel, tunnel washing, and the discharge of the fixed water-based firefighting system. So let's say that we provide the fixed water-based firefighting system that puts out, let's say, 1,000 GPM on our deluge system. The drainage system needs to be designed to deal with that 1,000 GPM plus the other sources that might be operating at the same time. So in a typical building where we're dealing with system sizing, we're mostly concerned about the size of that system itself, the fire protection system itself, and its impact on the overall cost of the project and the ability to provide protection. In this case, as we increase the size of the system, the fire protection system, we also increase the size of the drainage system. So it's a double impact. So what designers typically try to do in tunnels is they provide enough water to meet the performance objectives, so we don't have a fire that's out of control, as shown on the left, but no more water than is needed to meet those performance objectives, so we don't have a flood in the tunnel, shown in the photo on the right. So one method that's used very frequently to do that is a pressure regulating deluge valve, and it's used for a couple reasons. Tunnels that have fixed firefighting systems, typically longer tunnels, and so usually, and if we think about buildings that we do more commonly, and I think all designers know this very well, you go to get space for your pump and valves and all your other firefighting equipment, or tanks if you need them inside a building, usually kind of tough, right? Well known that design teams have a lot of back and forth between fire protection designers and the rest of the design team about getting room for fire pumps and tanks and anything else they need in the building. That's real estate that's being used up for that sometimes folks have other uses they want to use it for. So you do it in a building. Imagine the cost of a tunnel and trying to get real estate for pumps and tanks and whatever else you might need to supply that system inside a tunnel. Significant cost. So the idea is to provide as few of those pump rooms as possible and to supply the water potentially from a long distance away through mains. And so we have the potential for a significant friction loss through the mains. Also the potential for significant elevation change if we have a tunnel that's going down below, for example, a body of water. Right? So a tunnel that's moving below, like the Holland tunnel going below the Hudson River, it's got some elevation change as it goes down below the river from ground level down underneath and then back up, and that's going to create some differences in pressure also. So there's a chance under low flow conditions or no flow conditions that we could have extremely high pressures inside the fire mains in a tunnel. So that pressure regulating deluge valve has a couple of benefits in the way it does things. It restricts the pressure in a high pressure fire main down to something that the equipment in the system itself can work with. So let's say that we have a fire main that's 300 or 350 PSI, something close to 25 bar, and we have equipment on the actual deluge systems, the fixed water-based firefighting system, that's only rated for 12 bar, 175 PSI. You can use that pressure regulating deluge valve to reduce the pressure for that system from the high main down to the system pressure. The other good part is you can also use that valve to make sure that the system provides enough water for fire protection, but not too much. So let's say that we had a 75 PSI demand on the system. We don't want 100 because that's more water. That's more water that's being put into the tunnel that has to be dealt with by the drainage system. So we can use a pressure regulating deluge valve to reduce the output pressure, not just down to 175 psi for the equipment, but we could take that down to, let's say, 75 psi and get closer to the design demand so that we're not overflowing the deluge system in certain cases and putting more water into the tunnel that then has to be dealt with by the drainage system. So a couple of benefits to that. On Reliable's end, about a year ago, we came out with a pressure regulating deluge valve, or model DDV. And it is the highest pressure rated approved deluge valve on the market. So we have a 400 psi pressure rating on it, almost 28 bar. It's FM approved, available in sizes from 1.5 inch, 40 millimeters, all the way up to 6 inch, 150 or 165 millimeters. So nice size range. The valve has the highest pressure rating in the industry. So let's say that you're trying to space your pump rooms as far apart as possible. Well, this gives you the ability to do that better than any other valve on the market right now. The other thing to look at from a installation standpoint, tunnels are designed to last for a long time, right? They're substantial investments. Holland Tunnel, still in operation, built in the late 1920s. And I'm sure that tunnels that are being built today will be in operation for 50 or more years from now. Well, there's going to be some maintenance in that time. And as the regular inspections are done internal to the valve, typically required, you'll see that there's no trim connected to that valve cover. So it's easy from a maintenance standpoint. Pull off the cover, take a look inside, just bolt the cover back on and it's done. And it's really, relatively recent valve into the industry, but we knew what was out there and we designed something that provides some benefits over the existing products. So road tunnels, they're substantial infrastructure assets. They always have, that I know of, always have control centers, right? So there's a control center manned, staffed all the time, where the operation of the tunnel can be monitored, and it's a place for incident response. So whether it's a vehicle accident or a fire, there's someone there to watch what's going on, and they have a nice control center where they can change the traffic control signals, and they can operate the fixed firefighting system in tunnels where it's provided. So typically, a tunnel like this on a deluge system would have a on-off type deluge valve or remote resetting valve to allow the control center for the tunnel to turn individual systems or individual deluge systems on or off as needed during the fire incident. And that's done pretty simply. In this valve, there's a latching solenoid provided in this assembly. And it's a little bit different between FM and UL, where in FM's world, the power, the loss of power to the valve is not allowed to change the state of the valve. And so if something were to happen, communication or power lines were to somehow be disrupted during a fire event when this valve was open, it would stay open. That's a little bit different from a UL listed valve, where UL listed valve is allowed to stay open based on continuous power coming to the valve. And so if you had a many UL listed deluge valves with an on-off configuration and they lost power, the solenoid would typically close, which would also close the valve. And so our valve is FM approved, provided with a latching solenoid where the loss of power or signal to the valve does not change its state. The valve will continue operating even if the power or signal is cut off in the event of an emergency. So let's move on to another standard going around the world here a little bit, EU Directive 2004-54 EC. This came out, as you see, a few years after the series of fires that we looked at earlier. And it has a lot of the same sort of features identified by NFPA 502 in terms of emergency egress, structural fire resistance, fire hydrants. There's a little bit maybe more of a risk analysis discussion in the EU Directive. The one thing that's significantly different about it is that there's no direct requirement for a fixed water-based firefighting system. So a lot of times they'll still be provided based on that risk analysis, but it is, in terms of the water-based firefighting system, even more performance-based, I would think, than NFPA 502. So we'll still see fixed water-based firefighting systems in tunnels built to that directive, but you're not going to see prescriptive requirements for them. It'll be based on that risk analysis in the design. There's an Australian standard for tunnel fire safety, AS 4825. And again, it covers a lot of the same types of things that are covered in NFPA 502. Very nice standard. If you're working on a tunnel, really any place in the world, I think it's worth taking a look at this standard, AS 4825, 2011 edition. Covers a lot of the same things we talked about in NFPA 502. It also has requirements for providing fire suppression. So, fire suppression in road tunnels under the Australian standard, based on analysis of performance, they don't ever say it's absolutely required or absolutely not required. It's always based on that performance analysis, but they do indicate that it would typically be required, the deluge system, in tunnels greater than 120 meters or 394 feet. So less than half the distance where a tunnel fire protection system would be required by NFPA 502. And it's typically not required in tunnels less than 120 meters, 394 feet. That's, again, typically not required. Just like NFPA 502, even below the threshold, there are tunnels where you will see these systems required based on the performance-based analysis that is done, or the risk analysis that is done for that particular tunnel. There's a variety of factors that are identified in the Australian standard in terms of providing adequate discharge, zoning them appropriately, considering the effect of airflow and corrosion, for example. So all great factors. There are some example standards provided, including NFPA 15 and NFPA 502, along with some Australian fire protection standards for how that works. But in general, very similar sort of concepts to NFPA 502, maybe a little bit different in application, and maybe a little bit more performance-based even than what we see there. But overall, when you look at very nice standard, very well-written standard for fire protection in road tunnels. So let's look at the application of fire protection systems in a road tunnel. This is a case study of the new M4 tunnel in Sydney, Australia. So this was opened a couple of years ago now. No, about a year ago now. It's a twin tube design, and this is in part a safety feature where instead of just having one long tube with all of the roadway in it, there's two tubes, a lot of times connected by egress routes. There are 3 lanes in each direction for the most part. Now keep in mind there's interchanges at various points along the tunnel that may widen it out. And the tunnel itself is 3.4 miles in length times 2, right? So each tube is 3.4 miles in length. In total, it's 6.8 miles or 11 kilometers of tunnel. To get a sense of how this impacts the local economy and commerce around there, there are estimated 80,000 vehicles per day that use the tunnel. And in some of the planning, part of the intent of doing this was to take 10,000 trucks per day off of one of their local streets. So what's the other side of this? The other side of this is there are 10,000 trucks per day going through this tunnel that could have an issue. There are 80,000 cars per day going through this tunnel that could have a problem. And so there's a lot of potential for an issue. That's just the reality of it. And if there is an issue, there are a lot of residents, a lot of drivers who are going to get disrupted by that issue. And so there's been a lot of work done to make sure that tunnels, and particularly this one, stay safe to maintain that piece of infrastructure. It's a little brighter photograph of the tunnel, which opened in July, so just about a year ago, 2019. You'll see some of the traffic control devices, speed limit signs, lane closure signs, that kind of thing in the tunnel. Now, unfortunately, and you'll see here that the top of that tunnel, to avoid distraction, is all painted black. And so it's a little bit hard to see anything fire protection related in there, but we'll look at a photo in a little bit that has that. So on to fire protection systems. The new M4 tunnel has a deluge water spray system, actually has 517 of them, 100 feet each. They're designed to a 0.25 GPM per square foot density, or 10 millimeters per minute. And it was specified in order to reduce the number of branch lines required through that tunnel. It was specified with a minimum nozzle spacing of 17 feet by 17 feet, or 5.1 meters by 5.1 meters. And we'll talk a little bit about how this was achieved here in a couple slides. The deluge systems, or the tunnel, has a fiber optic detection system that can identify the location of a fire within the tunnel, and then the actual activation of the deluge system is done from the central monitoring station with individual control over each deluge zone using a remote resetting type deluge valve. So the nozzle selection, they were looking for a 17 foot by 17 foot coverage, like we talked about. So that's minimum of almost 300 square feet per nozzle with the density of 0.25, and that ends up being about 73 GPM, or 275 liters per minute per nozzle. There was not a nozzle on the market, nozzle available, that was really getting to that kind of coverage area, or that could provide a very low required pressure for that kind of flow. A lot of times when we use nozzles, we're using a nozzle with a K factor that's 2, 4, 6, something very low, like some of the medium velocity nozzles behind me. Now in this case, if we're trying to push 73 GPM or 275 liters per minute through a nozzle, we might want a little bit bigger K factor, larger orifice to make that easier. So Reliable came up with the TNL 280 nozzle. So this is a nozzle designed and developed for tunnel applications, although the reality is it's listed as an open spray nozzle. So if you find another application where you want spray characteristics like this nozzle provides, it's fine. Now, we developed it for tunnel applications, but it doesn't mean that you might not find other uses or projects that you're working on where it's useful. It has a K factor of 28 English units, GPM per PSI to the half, or K400 metric. It's UL listed as a spray nozzle for fire protection. It's also UL listed as corrosion resistant because it has a electroless nickel PTFE finish. And so a lot of times tunnel projects have corrosion concerns, not, of course, a climate controlled environment. And so one of the requirements was corrosion resistance. Now, one of the changes that you'll see coming up here soon, and if you have, for example, a tunnel that you're working on or starting to work on, nozzles are relatively easy to develop compared to sprinklers, and we're certainly happy to work with you if you're working on a tunnel project about any potential changes that might be needed or additional listings for this nozzle. For example, let's say you had a tunnel where they wanted stainless steel equipment. This nozzle, we don't make it right now in stainless steel, but we could. We just need the demand for it. We need the input. So one of the other things that we're doing is we're going to take our ENT coated nozzle and also provide a black paint top coat over top of it. And as you saw in the M4 tunnel photograph, a lot of the times the top of the tunnel will be painted black to avoid distractions to the drivers. And so we're working on updating our listing to allow a black paint top coat on our nozzle to go along with that. It's a photograph of the M4 tunnel during its testing. So you'll see a nice even distribution of spray along that tunnel in the deluge zone, along that roadway. There's a nice video, and some of the local news organizations have gone into the tunnel. They did a shutdown for testing more recently to do some additional annual testing where they shut down in the middle of the night and ran the systems each to make sure everything was still working. And there's some nice footage of that online on some of the local news stations from Sydney. The nozzle itself is listed again as a spray nozzle under UL 2351. Currently, we have a listing for installation at a height of 20 feet above the floor and another set of criteria for installation at 35 feet above the floor. Again, if you have a nozzle or if you have a tunnel that you're working on and it's going up to 38 or 40 feet and you need some assistance with figuring out how the spray is going to work in that, we're happy to provide that. There's a spray distribution graph in the technical bulletin 99 for this particular product. Shows the spray distribution with a 7 psi operating pressure and a 20 psi operating pressure, or 0.48 or 1.4 bar. Again, you'll notice that we're keeping the operating pressure very low for this system. Allows you to, again, stretch out the distance between pumps a very long way by keeping our minimum operating pressure very low. Let's talk about one other design question that comes up very frequently. And what is that? Well, we all see on the screen obstructions, right? And typically for a water spray system, NFPA 15, obstructions are dealt with as part of the design analysis without prescriptive rules, right? You consider what's out there and you decide if you can meet your design objectives with that particular obstruction, or you put in another nozzle. So that's one way to do it. One of the things that we're doing next is essentially allowing the option of, if you want to design using the extended coverage pendant spray sprinkler obstruction criteria from NFPA 13, you could do that also. And so we expect that to be updated in our technical literature later this month. But it's intended to be based on an engineering analysis or as an option of the designer if you prefer to use the NFPA 13 extended coverage sprinkler obstruction requirements, that would be fine also. On top of it, again, if you need design assistance with these types of systems, I'll put the number up on the screen at the end again, but please contact our technical services line and we're happy to provide that assistance. So let's watch just a little video of the TNL 280 nozzle spraying. These are 4 nozzles. On the floor, the markings down there, it's 10 feet in the center, 16-foot square next, and then a 20 by 20 square so you can kind of get perspective on it. These nozzles are spaced at 18 feet apart. We'll play it one more time. The pressure ramps up, and this is getting to about 20 psi. And we see a very, very even distribution of water throughout the coverage area of those sprinklers, and that's a big difference between a nozzle like the TNL 280 and a typical sprinkler. Typical extended coverage sprinkler is not usually this even in terms of its distribution, and something like, let's say, an ESFR sprinkler is typically not at all as even as this. They're more designed with a core and an umbrella. So this is different from a typical sprinkler, although we do see some tunnels that are designed with open sprinklers instead of nozzles like this. But this particular nozzle provides a very even distribution. And because of the large K factor and low pressure, the drops coming out of the sprinkler tend to be the nozzle tend to be relatively large, allowing them to get down through the fire plume and put water onto the fire and help suppress it. So the nozzle, TNL 280 nozzle that we developed and it's been used in several tunnels, has an extended coverage spacing to reduce the number of branch lines needed and the system cost. One of the advantages of this over some of the other options out there is that this is a pendant sprinkler where the sprinkler is centered within the coverage area. So it tends to have less impact from obstructions, for example, trucks, than some of the other options out there where the sprinkler is offset to one side of the coverage area, has to throw all the way across, potentially to get to the fire. The K factor of this nozzle being 28, largest K factor that we can put in a 1-inch threaded sprinkler, allows for a low operating pressure, large water droplets, and it's UL listed as corrosion resistant based on its testing and its ENT, or electroless nickel PTFE finish. So we've reached the end of the formal presentation. Let me point out that if you have any questions afterwards, let's say you, I don't know, have a question another hour or another day or sometime next week, or you work on a tunnel 6 months from now and you want to talk about this, please contact us at 1-800-55-RASCO, 1-800-557-2726, or by email, techserve@reliablesprinkler.com. So at any time in the future, if you have questions about this particular system or any other, please feel free to contact us at that number or email address. Now let's go through and look at some of the questions that we have here on the Q&A chat. Really, it can work in any deluge valve application, and whether that's a industrial environment like mining, oil and gas, any of those kind of places where you might want to, again, you might have high pressures there where you're trying to push water a long way in order to get to some protected item a long way away. So those are great applications for it. Transformer protection, we see these kind of valves used very often. Industrial sites, and really any deluge application, really very nice option for that. And that particular valve, the only trim we talked about this time was the on-off or remote resetting pressure regulating trim, but it's available in all the typical deluge trims: electric release, wet pilot, dry pilot. We have a dry pilot pressure regulating, and we have on-off without the pressure regulation as an option also. Again, whatever the project happens to need. So for the question about on the M4 tunnel, what size deluge valves they've used, that's 6-inch deluge valves. What we found is that some designers, and depends on the size of your deluge zone, right, which tells you, and your design density, how much water you're going to flow to that. Sometimes the zones will kind of verge on maybe wanting to move up to 8-inch, but we haven't seen that yet. In that we have a significant amount of flow, 3,000 GPM, that our DDV valve is listed for under its pressure regulating mode as part of our FM approval. And so we haven't seen a deluge zone yet that can't be handled by that. And the reality is that the deluge zones typically are not more than 100 feet long. And if we take a typical tunnel width by that length and look at the densities that are used in tunnels, typically not much more than a 0.25 density, we end up being able to flow that through a 6-inch valve just fine. And maybe there'll be some areas that aren't the main roadway, entrance exit spaces, something like that, where there's a smaller system and maybe a smaller valve could be used there. But for the most part, they end up being 6-inch valves. And well, almost in all the tunnels that we've seen so far, with maybe some limited areas that are smaller valves. So going on to some of the questions in here. What's the typical demand area for the system design? So the demand area for one of these water-based fire protection systems will be the size of the whole deluge zone. Since it's a deluge system, typically those deluge zones are about not more than 100 feet long, 30 meters. And so the demand area would be the width of the tunnel by times the length of the deluge zone, typically not more than 30 meters long. Sometimes they'll get a little shorter, depending on how much control and how much water demand you want to have, right? I mean, there's a design, some thought to be given to the design where if you want to have a smaller water supply, one way to do that is to shorten up the size of the zone, reduce the demand with that. On the other hand, that would increase the number of deluge zones and the number of deluge valves needed. But sometimes being able to cut back on your water supply need, it's worth doing that. It's very beneficial, and increasing the number of deluge zones is not a big deal compared to the water supply savings, but it's something to be considered in the design. So then there's a question about whether prescriptive design is valid and only performance design is allowed. That's the way that the tunnel standards are typically written, as very performance-based. It's not that there aren't prescriptive requirements, and it's not that they aren't valid to some extent, but the reality is there's nothing in any of these standards that tells you prescriptively exactly how to design and lay out your fire protection system for a tunnel. And so a lot of that does end up being performance-based because that's the way those particular standards are written, those tunnel standards. And I think the reality of a lot of tunnels are they're such major projects that there are design teams working on them for years in order to develop those designs and get them approved and make sure that everybody's happy with it. And the reality is that the designers, the AHJs, everybody involved wants to sleep well at night. They know they're putting a system out there to protect people, protect property, protect a major part of a city, and they all want to feel good that what they're putting in is going to do that. And so, performance-based design is a lot of times used, in accordance with those standards, because it gets a whole lot of analysis of several systems working together, the egress systems, the traffic control systems, the ventilation systems, along with the fixed firefighting system. That's typically done in a performance-based manner. That's the last of the questions that I saw, although let me check back one more time and see if we have any more that came in. Okay, so we have some questions that came in. Additionally, I'm going to go through as many of these as I can get to in the next minute or two before we end this, and then I can answer the rest maybe in the chat here. Is it preferable to provide a water curtain between zones? Typically not. They're deluge zones, and so they're operated in many cases manually as needed. Typically, these tunnels have TV systems, video monitoring systems that allow them to see where the incident is, get the correct zone on, or sometimes they'll operate multiple zones at the same time. But usually there aren't water curtains between the zones because it's all deluge systems that are not operating off of automatic sprinklers. Okay, and then there's a question about the height of the tunnel. The tunnel's higher than 13 meters. Do we need multiple layers of nozzles? No, that wouldn't be the case. What we would need to do in that case, and if that occurs, you're working on a tunnel and you find something that's outside of the existing listing, you're welcome to contact us at the technical services line, and let's have a discussion about how to get that addressed. Maybe the solution is we would do some, look at it internally. Maybe the solution is that we would do some additional listing work. We'd have to see. But I think you would always try to do that with one layer of nozzles up at the top and protect everything down below. So we've reached the limit of our time here today. I'm going to go through and answer the rest of the questions that we have. Let me thank all of you for attending. We appreciate it very much. Thank you very much for joining us here. We hope that you found it valuable. Expect another webinar to come out here in another 2 weeks. I think next time we're going to look at data centers and some of the protection options for those spaces. But again, thank you very much for attending. We appreciate it, and have a good rest of your day.